Hello everyone. In this video, we will talk about conditional probability and independence. Before we start, we said if we have a sample space that contain all possible outcomes of an experiment, and we defined event A here that contain all possible outcomes, desired outcomes for event A to happen, and they ask you what is the probability of A, then you will say the number of outcomes inside this circle divided by the total outcomes in the sample space, or the area of this circle divided by the total area of the sample space. Now if there is another event, and let's call it B. Now I told you event B happened. What's the probability A happened? So that's the simple. So that's what we call conditional probability. I already told you that event B already happened. So I conduct the experiment and I saw the outcome and I told you event B happened. Can you tell me what is the probability that event A also happened? Now, since I already give you this piece of information that event B happened, that means the possible data point has to be somewhere here, since I already told you B happened. So these are the possible outcomes inside this circle. Now, for event A to also happen, the outcome has to be inside this region for A also to happen. So what is that possibility? Then it is the area, or it is the probability of the intersection of A intersect of B, so that's the area here, divided by the total probability, which is this one, the whole area of this section. And this we call the conditional probability. So let's look at this example. In a process that manufactures aluminum cans, the probability that a can has a flaw, so we have a can here, has a flaw on its side is 0.02. So let's say this is event A, a flaw in the side, and is 0.02. The probability that a can has a flaw in the top is 0.03, and let's call this event B. In the top 0.03. And the probability that a can has a flaw on both sides, that means the intersection, both sides, probability of A and B is 0.01. Okay, now what's the probability that a can will have a flaw on the side given that it has a flaw on the top? So I pull a can and I saw there is a flaw on the top. So can you tell me what's the probability that it has also a flaw in the side? Well, if we draw the Venn diagram and B is this one, A is this one, the probability of B is 0.03, A is 0.02, the intersection here is 0.01. So it is given that it has flaw on the top. So it's given that B happened. It has flaw on the top. And they want to know what's the probability it will have a flaw on the side. So what's the probability A? We follow the conditional probability, which is probability of A and B divided by the probability of B. Probability of A and B is 0.01 divided by probability of B is 0.03. So this one is 1/3. So there are 33.33% chance the can will have also a flaw on the side. Okay, now independence, if you have two events, A and B, if you know anything about B and it doesn't tell you anything about event A, if it will happen or not, then we call them they are independent. That means there is no relationship between them. There is no mechanism that A affect B or B affect A. And in engineering we say if this is system connected here, if some error happened here, it will not affect this subsystem. Then we say these two subsystems are independent. So if they are independent, let's say this is A and this is B, what is the probability A happened given that B already happened? B tell you nothing. Just by knowing it is B already happened or didn't, it won't tell you any information about A. So this is exactly the same as the probability of A. So if this has a 20% chance of error, just because this worked perfectly or corrupted, that probability here will be same thing, 20%. And that's what independent means. Now, if A and B are mutually exclusive, are they independent? No, they are not independent. If A and B are mutually exclusive, that means if A happened, B cannot happen. That's what mutually exclusive. So that means if I already know what happened to A, it's telling me some information about B. Okay, multiplication rule. We start with the conditional probability. Probability of A given B. We say that is probability of A intersect B divided by the probability of B. Now if I do cross product, imagine here is 1. If I do a cross product, then this is probability of A intersect B equal probability of B time probability of A given B, as long as probability of B is not 0. Now if A and B are independent, then this probability here will be just probability of A times the probability of B. So for A and B to happen, then it is the probability of B times the probability of A. And this is the same as I said, if I have a system here, the probability of corruption is 0.2 and the probability of corruption here is 0.3, and this is system A and this is system B. What is the probability? Both systems will go wrong. So that means what's the probability of A and B? So that will be, since they are independent, it will be 0.2 times 0.3, and this is 0.06. So there is a 6% chance both systems will go wrong. If you have n events, A1 to n events, and they are independent, then the probability A1 happened and A2 happened, and n happened, it's this probability. In example 10, of the microprocessors manufactured by a certain process, 20% are defective. So probability of D defection is 0.2. 5 microprocessors are chosen at random. So you took a sample of 5. Assume they function independently. What's the probability that they all work? That means these 5 microprocessors here, for all of them to work, it will be, well, the probability for this one to work is 1 minus 0.2 is 0.8. Same thing, this 0.8. So the probability for all of them to work is 0.8 times 0.8 times this, times this, times this. So that is 0.8 multiplied 5 times. Let's look at the law of total probability. Let's assume you have all these events. Event A1, which is this one. Event A2, which is this one, and A3, this one, and so forth, all the way to event A7. And you can think of this event is transmitting 7 symbols. So I have symbol A1, symbol A2, symbol A3, all the way to A7. Then we have event B, which is here. You can think of it as the received symbol is corrupted. So you are transmitting these 7 symbols through a channel, and event B here, it's either received correct or received wrong. So let's assume event B is the symbol received wrong. Now you can think of this here. You are transmitting the symbol A6. This area is the probability that this symbol was transmitted correctly, and this area here, the probability that the symbol was corrupted. So now I am interested in the following. For this channel could be coaxial cable, the medium where you transmit your signal, or fiber optic or wireless, and I am interested on what's the probability of B. Probability of error. So in this case we can think of it as follow. It's the probability I transmit A1 and there was an error. In this case there is no error, 0. Plus the probability I transmit A2 and an error happened, which is this area. That means the probability the data were here. Plus the probability I transmitted A3 and there was an error. That means the data has to be somewhere here. And that is what is this statement here. So if I want to find the probability of B, it's the probability I transmit symbol A1 and it arrived corrupted, plus the probability I transmit symbol A2 and it arrived corrupted, probability I transmitted symbol A3 and it arrived corrupted. So if you do these, then you will get all these gray area. And that's what this equation, what it means. Now I can rewrite this equation in a different way using this conditional, what we showed here. So probability A and B is probability A times probability of B given A. So we can rewrite these here. The probability of A1 and B is the same as the probability B happened given that A1 already happened, multiplied by probability of A1, and that will be the same as this one. Same thing here, this probability will be probability of B error happened given that you transmitted AN times the probability you transmitted AN. Now let's see how we use this total probability law to solve certain problems. There are a lot of applications for this in communication, but let's look here for mechanical problem here. Customer who purchase a certain make of car can order an engine in any of three sizes. Of all cars sold, 45% have the smallest engine. So let's say engine small, engine medium, engine large. And there are 45% of small engine were sold, 35% medium, and 20% large. So I can draw this population, 45, this one, so small, medium, large. Of cars with a small engine, 10% fail. So let's draw the failing event. They said this is 0.45, medium is 0.35, large is 0.2. Of cars with a small engine, 10% fail. So this is here 10% fail, 0.1 within the 2 years. 12% of the medium size failed. The medium size is here, so 12%, so that is 0.12. 15% of the largest engine, 0.15 failed. What is the probability that a random chosen car will fail an emission test within 2 years? So let's represent this event failing F. So they want the probability of failing. We will be using this. So this says the following. Probability of failing is the probability of failing given that it is a small car times the probability of selling a small car plus probability it failed given that it's medium car times the probability I sold a medium car plus probability of failing given that it was a large car times the probability of large car. So this one here is the probability of small car. This is the probability of large car. This is the probability of selling a medium car. This one here, probability of failing giving that it's a small car. So that's this one here. This one here, 0.15, is the probability of failing given that it's a large car. And the last one here is the probability of failing given that it's a medium car. So I plug numbers here. Probability failing given that small car is 0.1 times probability small car is 0.45. Probability it fail given that it's a medium car, that's this one here, 0.12 times the probability of medium is 0.35. Probability failing and it's large is this one times the probability it is large, which is 0.2. So the answer should be 0.117. So that means 11.7% a chance a randomly chosen car will fail an emission test within 2 years. Okay, this is the step we just explained here. In Bayes' rule, we start with the conditional probability. Probability of A given B is probability of A intersect B divided by the probability of B. It doesn't matter if probability of A given B or probability of B given A is probability of A and B divided by the probability of A. So if I do a cross product here, this is the same as probability of A and B equal probability of A given B times probability of B. Same thing here, if I do a cross product here, probability of A and B equal probability of B given A times probability of A. So these here are the same. So these two here has to be the same. So then I can rewrite it as probability of A given B times probability of B equal probability of B given A times probability of A. Now if I want this probability by itself, I can divide both sides by probability of B. So probability of A given B equal this. And that's Bayes' rule. What does it tell you? Let's say B is an error. So I know the received data or the car emission test failed. What's the probability the car was a large car? Or in communication, if I told you there was error in the received symbol, so that's B, error, what's the probability that the transmitted symbol was 0 or 1? So I already gave you the information. A failure happened. Now I want to know that failure, is it because the medium car or the small car? These are the applications of Bayes' rule. We already showed this is true by following the math here. But let's see if we can visualize the meaning of these equations. So imagine you are doing an experiment and you saw the outcome. So you already know the outcome is in event B. So you know B happened. So that means the outcome, if B happened, then the outcome has to be inside this region. Now I am interested, what's the probability this outcome came because A happened? In this case, only outcome in this region I am interested in. If I already know B happened and I want to know what's the probability that it happened because of event A, then the outcome in this region are the desired outcome. But all I have is B happened. So all possible outcomes are inside this circle or region. So that's all I know. The outcome can be inside this region, but my desired outcome is this part of the outcome. So if I want to find the probability, it will be this area here, this area, which is these equations, divided by the total area, all possible, which is this probability. So you already know B happened, so you have this area. Now, if A happened, then the outcomes has to be in this region, which is this. And that's how we visualize it. To move from here to here, if I expand the probability of B, the probability of B error happened is the probability of error happened giving that A happened times the probability of A, plus probability error happened given that the complement, not A happened, something else, A complement times the probability the complement happened. And I can replace this one here by this, which is here. And this one, I use the total probability law. These equations came from the total probability law, which is this one, Instead of A1, it's A2 is A complement. Now, in this case, we just showed two possible events, A and a complement, but there are a possibility where you have more than just two possible events, A and the complement. You may have something like this. You may have the sample space consists of three sub-sample or event, A1, A2, and A3. You can think of these medium car, large car, small car, or transmitting a symbol A1, symbol A2, a symbol A3, and this is be the region, the failure of the car or of the transmission. I know there is a failure happened, but I want to know, is this failure because of event A1 or A2 or A3 or AK? So we use the Bayes rule theorem. It's the probability failure happened given that AK causing it, time what's the probability AK happened, divided by probability of failure. This is just the probability of failure. But I am using now the total probability, which is the same as this one. But here I have only A and A complement. Here, A, I have them all the way from 1 to N. In this case, there are 3 of them. I can have 5 of them, 6 of them. For example, I may transmit 0, 0, 0, 1, 1, 0, 1, 1. So then this will be, and let's assume the probability of transmitting each one of them is the same. So that will be here, 0, 0, 0, 1, 1, 0, 1, 1. They have the same area, the same probability. Probability of 0, 0 transmission or probability of 0, 1 transmission and so forth. And maybe the channel is more vulnerable to a simple 0, 1 or 1, 0. So if I send 0, 1, I have a larger probability of error versus if I send 0, 0, and the large probability of error if I send 0, 1, and the small if I send 1, 1. So then this region will be the probability of error given that you transmitted 0, 1. So that's why this summation, it depends on how many events you are studying, 4 or 10 or 20. So that's the Bayes rule theorem. And remember the denominator here is just the probability of the event B. So let's look at an example. The proportion of people in a given community who have a certain disease is 0.005. So that's 0.5%. So let's draw our population. Probability of disease 0.005. Probability of no disease, healthy people, that's the complement, will be 1 minus 0.005. So that's 0.995. If a person has the disease, the probability that the test will produce a positive signal is 0.99. So that's the probability if the person has a disease. So given the person has a disease, the probability that the test will produce a positive signal. That means the test correctly identified. So let's define positive, correctly identified positive here is 0.99. So I'm carrying the test. If the person has the disease, then the test will correctly identify or diagnose the subject, 99%. If a person does not have the disease, the probability that the test will produce a positive signal is 0.01. So the probability, given that the person does not have a disease, so that's the complement, healthy, and the test give positive, say the person is sick even though he's not, that probability is 0.01. So now they are asking here, if a person tests positive, so the given information is the person was tested positive, what's the probability that the person actually has the disease? Let's define the event when the device diagnoses the subject as positive, regardless if the subject is healthy or not healthy. And let's draw that event, positive diagnosis. So If the person has a disease and they diagnosed it positive, is 99% correct. So that will be something like this. And the area here is 0.99. This 1% is when the subject healthy, no disease, the complement of disease, which is this area, and diagnosed positive. So that would be this area here, 0.01. In medical terminology, they call these true positive. That means the device is correct in identifying the disease in the subject. And these, even though the subject is no disease, D complement, no disease, healthy, but it identify it as positive. So we call this false positive. So now we tested the subject and the device said the subject has a disease. What's the probability that the subject actually has the disease? So we're going to use the Bayes rules, and this is the following. Probability a person has a disease given that the test is positive is the same as the probability the person has the disease given that disease and the test showed positive times the probability of the disease divided by the probability of positive event. And I will use the total rule to express this probability of positive diagnosis. So that would be probability of positive given that D times probability of D, and this will be total probability is probability positive given that the person has a disease times the probability of the disease. So that will be the green area plus the blue area, probability of positive and the person is healthy times the probability the person is healthy. And this will be, this probability here is 0.99. This probability is 0.005. The whole thing here is the same as in the numerator, 0.99 times 0.005 plus this probability positive diagnosis giving that the person is healthy is 0.01 times the probability the person is healthy, this one is here, 0.995. And if you calculate this probability, it will be 0.3322. So there is 33.22% chance the test will show positive and the person has a disease. Now in medical field, when you design devices, there are a lot of criteria how good is your device. It's not how accurately the device can diagnose the patient, but also how much error the device can make in telling a patient you are free of cancer, but he has a cancer. Or you have a cancer and when the person does not have a cancer. So when you do the design of medical devices, you follow these criteria. True positive, the number of cases correctly identified as patient. False positive, the number of cases incorrectly identified as patient. True negative, when the patient is healthy and the device said he is healthy. False negative, when the patient is sick and the device says no, he is healthy. So this is the terminology. Now, when you buy medical devices, they specify accuracy, sensitivity, specificity. And accuracy is the ability to differentiate the patient and healthy cases. That's how accurate is the system. And this is the equation. Sensitivity, the ability of the system to determine the patient case correctly. That means make less mistakes in telling a healthy person you are sick or a sick person, say you are healthy. And this is the equation we use. Specificity, the ability of the device to determine the healthy cases correctly. It may make a mistake with the sick people, say they are healthy or not. But for the healthy cases, it's very, very accurate. So usually there is conflict. You increase accuracy at the expense of sensitivity or specificity. But as a medical devices, when you design a system or a device to diagnose certain disease, you want that device to be as accurate as possible to identify a sick person. It's okay if a healthy person and by mistake you say that he is sick, because you can do a further diagnosis to eliminate that error or mistake. But you don't want the device to tell a sick person you are healthy. If the device says healthy, you are not going to carry out further tests to make sure the person is healthy or not. So remember, accuracy, sensitivity, and specificity. So you improve one at the expense of the another one. Okay, I will stop here. And the next video, we're going to start with the random variables. Thank you.